whatever. There I am. So, one of the reasons you can't see your breath right now is because we've all got masks on. So, even if it were really cold, I don't know, has anybody been out in the cold recently and been breathing and saw the stuff rising up from your mask? So you can see it, it's visible. What's that?
Usually when it's really early in the morning.
Really early in the morning? Yeah. So as it gets, well, as the weather changes, we'll see that more. And so the first question is, why can't we see it now? Even if I took my mask off right now, I just went into the air, you'd all be like shocked. Look at him blowing his breath into the air with the mask on. But why wouldn't we be able to see it? What do you think, Anna?
Temperatures are too close together to be like for it to be visible.
Excellent answer. So when you say the temperatures, what two temperatures are you comparing?
Hot and cold.
Like in your body and outside your body?
Yeah. Yes.
Yeah. So the air that's in my mouth is hot, and it comes out into the room air, which is cold, but not cold enough, right? If it were really cold, then you could see my breath. So somehow you see it when the warm, moist air from your mouth goes into the colder air around you. Number two, when we see our breath, what are we actually seeing? And I talked about this last 2 classes ago. Unfortunately, it's not on the video because that was all silent. But when I had the flask and it was boiling and you could see this stuff coming out, what is that? But there are multiple ways to answer it. Like first, what is the substance that we're seeing? Anyone? When you go, when you see this little cloud, is that gold or arsenic or what?
Air.
Yeah, well, there's a lot of stuff in air.
Water.
Yeah. So there are other things in air that, under certain conditions, we could see like that, but it's water. So there's water in our breath, and when we blow it out under some circumstances, you can see it. Now, under some other really, really, really odd, special circumstances, you might actually be able to see the nitrogen that you're breathing out. Most of what we're in right now is nitrogen. 80% of the air is nitrogen. Nearly 79%. Around 20% is oxygen, and then there's this other stuff. But the water is what we see. There's only a tiny bit of water in the air. All right, so we're seeing water. Now this is the one that gets people. And it's intentionally a trick question because we just got to get past this. When you look up and you look at a cloud, which is basically the same thing as your breath. This is just a cloud. This could be a cloud of your breath that you just went and breathed out. Is this a solid, a liquid, or a gas? Don't blurt it. Just think about it. And I'm just going to want a little show of hands, just so you have some skin in the game here. All right. Now, I'm going to make one of these in the air in here in just a little while. Not using my breath, but doing it a different way. And when I do that, how many people think it'll be a solid? How many people think it'll be a liquid? How many people think it'll be a gas? So there are about 3 people thinking, and then the rest of you just are not, you're just ashamed to share. I won't make fun of you, I promise, if you get the wrong answer. The fewest people, we had the lowest number actually get it correct. The answer is, this is a liquid. This is a liquid. And sometimes, I've gone out on my deck on a cold night in the fall and just noticed it was really humid out, and I can see this, wake up there, Reagan, and you can see this cloud in front of you, and I can almost see little tiny particles. So when I'm looking at these, these are actually little droplets of water in that cloud. And the key is, a gas is invisible. Almost all gases are invisible. So what's between my hands right now? That's a gas. If you can see it, is not a gas. There are a few exceptions to that, but generally, it definitely holds true with water and most other things. If you can see it, it's either a liquid or a solid. So in the winter, if it's 20 below and you blow your breath out and this little cloud of water droplets comes out, it's not going to be a liquid. What's it going to be? What happens to liquid when it's 20 degrees below zero? Freezes. So these will be little crystals of ice. And then really quickly, actually, it'll disappear. So it'll turn back into a gas, even though it was a solid, which is kind of strange. We could talk about that some other time. So any cloud that you see is made of, it's either liquid or solid, not a gas because you can't see a gas. When I blew my breath out right now, I'm doing it through my mask, but it's coming out, and there is water there, but that water is a gas, so you can't see it. If the air was really cold, what happens when you cool a gas down? What does it turn to? Does it turn to a solid or a liquid? It turns to a liquid first, and then if you cool it more, it turns to a solid. So when we see that, we're seeing lots of little liquid droplets. All right, I made this video last night because I can't do this in the classroom. Did this, it's kind of creepy looking, in my kitchen, but what I did is I had a flashlight shining like that, and you can see the droplets a lot better when there's light shining on them. Again, kind of weird. Nope. Looks like a horror movie so far. Didn't I run into this before, that somehow playing the video was really slow? I wonder if it's something about trying to stream and show videos at the same time. It did work eventually though, right? Maybe I should just let this sit here and load for a while. Or I think what I'll do is I'll email it to myself, and then I'll just open it up out of my email and show it to you. Oh, really frustrating. I guess that means the other video. Oh, you know what I'll do? I'll show it to you on my phone. So I guess I should quit trying to show you. I wonder if part of the problem is I'm streaming from YouTube right now, or streaming on YouTube. And maybe my doing stuff in YouTube while I'm streaming on YouTube is just a bad idea. Here, let me go to my pictures. There I am. I did several of them. All right. Oh, hold on.
Please come to the main office. Please report to the main office. Thank you.
All right. So first I show you that just regular breathing doesn't do anything. But now that wasn't my last one. My last one was better. Here, let's watch this one. So regular breathing. And it only comes out for a second. You have this little cloud, and then the cloud evaporates and turns back into a gas. Oh, that's an unfortunate way to stop the video. Okay. So we go to here again. Could you tell from the look on my face what I was doing? What?
Something to do with holding the breath?
Sort of, but I looked like I was kind of straining, didn't I? I should have. I wasn't just holding my breath. I was actually squeezing my breath. So I don't know if you've ever. There's a thing down here about diesel, or it says a fire piston. Has anybody ever heard of a fire piston? It's a thing you can use to light fires, and we had one. We have one in the physics department, and I was going to demonstrate how it worked for you, and I can still demonstrate how it works. It just doesn't work because the seal on it is no good anymore. So this is the fire piston, and you take a little bit of this cotton and you put it down in the bottom of this thing, and then you push down really fast. Now, if I had good O-rings on, show you what I mean by O-rings. Right in these grooves, they're supposed to be rubber rings, and they form a seal, but they broke last night. So normally to pull this out, I've got to pull really hard, and to push it in, I've got to push really hard, because when I push down, the air gets stuck in there. So as I squeeze really hard, what I'm doing is increasing the pressure, and anything that's in there catches on fire because the temperature actually changes. So what I was doing in that video, well, the video on my phone, when I was doing this, is I was squeezing the air in my mouth, which is heating it up. So normally my warm breath goes out in the room and doesn't cool off much. In cold weather, my warm breath goes out into the cold and cools off a lot. So what I did was I made my breath super duper hot, so when it would go out, it would cool off a lot. And I'll show you another way to do this. Instead of using my breath, I'm going to use this bike pump. I'll point it over here. Turn like that. And I made this. This is something we use in physics to launch things going really fast. I put a PVC pipe in here, and you can put a little piece of potato in the pipe, you can put paper in the pipe, you can put grapes in the pipe. Grapes are awesome. And if you pump this up and then suddenly you turn the valve and you let the pressure off, you can shoot grapes out of this 250, 300 miles per hour. But that's not the point right now. Alyssa or Reagan, let's see, and actually, whoever's watching this, I'm going to leave the picture because I want Alyssa to hold on to this while I pump it up. And I'm asking you because you have safety glasses on. You're holding the bottle while I pump it. It's totally safe.
See, you say that.
Here, now put your hands right here because then you'll be able to feel it. Okay. And I can pump. So people at home, I haven't disappeared. I'll come back into the picture in a second. I'm pumping this bottle, and if I pumped it to probably 180 psi, it would explode in Alyssa's hands, and that would be really bad. But I'm only going to pump it to about 45 psi. Now, as I do this, it's getting harder, but is the temperature changing at all? It's getting hot, yes. So this is warming up, warming up, warming up. And if I could inflate it really fast, it would get much hotter. So all I really want to show you today is that when you heat something up, when you compress air, when you increase the pressure, when you squeeze something, it heats up. You'll have to believe Alyssa. Did it get hot? Yeah. And actually, RJ, you can touch it. You can probably still feel it. It feels warm, right? Now, back over here. And I don't know if you can see, I put a little bit of water in it. It's got some water droplets in there. So when you heat up water, liquid water, that makes it change state or change phase. Is that liquid water in there going to turn to a solid or a gas if it changes phase? If I'm heating it up, what does that turn it to? A gas. So what I just did is by compressing this, heating it up, I evaporated some of that and turned it into a gas. Now when I release this valve, it's going to come shooting out. If you compress air, it gets hot. Guess what happens when you let it expand again? It gets cold. And this is how refrigerators work and how air conditioners work and heat pumps work. There's a compressor and an expansion valve. So when you compress, you heat things up, then you let the heat go away. That's what I'm doing right now. Do you feel it now, Alyssa? Is it as warm as it was a minute ago? No. So compressed it and heated it up, and then the air in the room sort of took that heat away. and my hands and her hands took the heat away. So now it's cooler, but when I release this, it's going to get even colder. So I guess the point is not to tell you about air conditioners, but to show you this. And you'll see this better if I shine a bright light. And that's what this old overhead projector is for. Turn this off. Works best if there's a black background, and I don't really have a black background, but when I open this valve, you should see a couple of things happen. It's probably going to suddenly get really foggy in here because suddenly the air is getting really cold and a cloud is forming. And you'll also see it come out there. And if I had my hand right here, which I can, I'd feel it get cold. Does anybody? Well, no, then you'd be in the picture. So let me just do this, and we should get a nice, like, see your breath thing. This is so much better than I can squeeze the air in my mouth. So, looks cold, right? And it is cold. You're feeling this now. Feel that, RJ? Feel that? Yeah. All right, so the whole point is, we'll come back to this next class and maybe do some notes on it and explain why, but when you compress something, you heat it up, and when it expands, it cools off. So when we get to stars, if you have a star, guess what's squeezing the star in? Anybody know? Gravity. And when gravity squeezes the star in, what does that do to the star's temperature? Makes it hot. So that's not actually where they get their energy, but that's where the heat comes from that can start the nuclear fusion off. And we'll get back to that later on. So the rest of class today is mostly just catching up and tying up loose ends. So put my picture back up here. Last night's homework. We're going to go over last night's homework, and I made a histogram of last night's homework. Should have asked you if you knew what a histogram is. So this is an example of a histogram. The scores don't really matter. It's just I was curious to see how well people would do. The way a histogram works is that you have number of students on the y-axis. Again, putting myself in there. So right here, this is the number of students, and then these are scores. And Google Sheets does the histograms kind of funny. What this means is one person got a score between 1 and 3. I don't know if that was a 2 or a 3 or a 1 really, but in that range, one person got that score. And somebody scored between a 3 and a 5. Most of the people who did this got between 5 and 7, so probably around 6 right out of 10. 2 people got between 7 and 9, and then there was one person who got a 10 on the quiz, one perfect score. One kind of interesting thing, if we count all the people, 1, 2, plus 5 is 7, plus 3 is 10, plus 1 is 11. Only 11 people did this. Some of you didn't do it. Shame on you. You should make sure you do this. Although, what's that?
Was that the Google?
Yeah.
Okay.
Yeah. So do that and submit it. I think one person did it and didn't submit the thing because I couldn't get a score for it. And your score is, I'm not going to record the score in PowerSchool. All these people, everybody got 100% on this assignment. Let me go back to here. We're going to do the quiz together right now because it doesn't explain why you missed what you missed. So let me go to temperature. This is it. All right, so we've got this sealed jar containing air. The next few questions refer to this. This is a glass jar. Is this glass jar going to be like a balloon where it can just inflate and deflate? No. So one thing we know about this jar is that the volume is going to stay the same the whole time. It's not going to get bigger or smaller. It's also sealed, which means nothing can get in or out. So what else is going to stay the same other than volume? The mass and the density. So this is going to be the same size with the same stuff in it. So volume, mass, and density and weight, they're all going to be the same. So here, what will happen to the speed of the molecules when it's cooled down? Everybody should be able to get that. You cool them, they slow down. And what happens to the speed of the molecules when you heat it up? Speed up, all right. So those should have been 2 gimmies. I don't know how somebody got a 1 on this. No offense if you got the 1, but you should have gotten those 2. And then you should have at least guessed another one right. My goodness, there are 3 choices. Even if you randomly guessed on this, you should have gotten them. More than 1, I don't know what happened there. Maybe they were trying to get a 1. Or maybe they just did 1 and submitted. What will happen to the pressure inside the jar when it's cooled down? Okay, this is the first harder one. If I cool this, if I put it in a freezer and I measure the air pressure in there, is it going to increase or decrease or stay the same? Decrease? Yes. And the reason it's going to decrease is because it's caused by the particles moving around. If they slow down, then they're not going to push against the walls as hard anymore. If they're going really fast, they're going bam, bam, bam. But if they're going slowly, push, push, that's lower pressure. So the pressure will decrease. Part of these is just being careful. Sometimes you'll read it and you'll think, oh, the jar's heating up, but it really says cool down. What will happen to the mass of the jar if it's heated up? I've already talked about this. If it's sealed, can the mass change? No, not unless you break it and throw away some glass, so it's not going to change. What will happen to the density of the jar when it's heated up? And assuming the size doesn't change, so you got the same stuff in the same amount of space, it's not going to change how crowded it is. So that's going to not change. So that was for the jar that can't expand. Now the balloon is different because the balloon can expand. Rubber balloon can get bigger, can get smaller. Suppose you put the balloon in a freezer and cool it down, what happens to the mass? Stays the same because mass is stuff, and if this is tied off, that's not going to add any stuff to it or take away any stuff. So the mass stays the same. What happens to the volume as it sits in the freezer? This is a little tricky. Is it going to stay the same size? Is it going to get bigger or get smaller? What did you say?
It'll get smaller.
Get smaller. And really, I put these a little out of order. The reason they get smaller is because of the, what's the word I'm about to say? It gets smaller because something else decreases. Pressure. So, and I guess the pressure decreases because of the temperature. You put this in the freezer, it cools off, those bouncy molecules inside slow down, so they don't push as hard anymore, so the pressure decreases, and when they don't push as hard, the walls of the balloon can squeeze in. If they start pushing harder, the walls of the balloon push out. So what happens to the volume? Decreases. Just about everything in the world, when it cools down, it shrinks. We're having a garage built right now, and in the floor of the garage, they're cutting little cracks intentionally. They cut grooves across the floor. Does anybody know why? It's not because I want cracks on my floor. What do you think? So it'll drain? That's a good idea too. And in fact, that might help the water kind of drain out to the edge. But it's not that. It has to do with the concrete itself. When it starts to get really cold, if I leave the garage doors open this winter and it gets really cold, is that concrete going to get bigger or smaller? Smaller, it's going to shrink. And then in the summer, when it starts to heat up, it's going to expand. So when concrete heats and expands, it cracks. And if you cut cracks in it, it'll just expand, and you're going to have cracks one way or another. But if you cut the cracks ahead of time, you can choose where it expands and shrinks. So we don't have them here, but a lot of states have concrete highways, and on the highways, when you're driving, you hear boom, ba-dum, 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 because they have these joints called expansion joints all the way along the highway, so that when it expands and shrinks, there can be a little gap of air there instead of weird cracks forming and destroying the road. So my point is, everything shrinks when it gets colder, with the exception of water when you freeze it. Water expands. What happens to the density? So if it's getting smaller and it's got the same stuff in it, is it more crowded or less? More crowded. So that would increase. What happens to the pressure of the balloon as it sits in the freezer? So pressure is caused by the molecules inside. So is there going to be more pressure or less? Less. So we can rule those first two out. And then we've got air pressure decreases because the molecules of air lose mass, and air pressure decreases because slower molecules push outward with less force. First one or the second one? Second one. It's this one. And I think this is the last one. What usually happens trapped in a sealed rubber balloon when you heat it up. So this is kind of putting it all together. Volume increase, so you've got a balloon, you heat it up. Volume increases, but density and pressure decrease. Mass and pressure, I'm just going to cut to the one that I think is right, and I'll tell you why. So it's not this, because when you heat it up, there's more pressure, so it wouldn't be that. The second one, mass and pressure increase. No, it's sealed. So the mass can't change. So I can rule that one out. Volume, density, and pressure all increase. Well, it would get bigger, but it wouldn't get more dense as it expands. It would become more spread out and less crowded. So it must be this one. Volume, that's how big it is, increases. Pressure increases, but density decreases. That's it. Let's see how we did. I've done this before where I got them all right and it says my score is a 7 out of 10, and that means I screwed up the answer key, but this time I didn't. So it was right. Okay. So hopefully, you feel like you can get a better score on that now? Okay, that's the whole point of what we're doing here. To learn things you didn't know before. So we did that, brief lesson. I've pretty much with the warm-up, I've shown you how pressure changes can cause temperature changes. Let's just review that. If you squeeze something, does it get hotter or colder? Compress things, hotter or colder? It's hotter. If you let something expand, what happens to it? It's colder. All right, you got it. Yes? Sure. And we'll be, pretty soon here, we'll be starting the quizzes, so don't take too long. All right, golden remote students. Well, next class it says making clouds in bottles. We'll be doing that sometime soon. We'll see how long it takes us to get to that. Golden remote students, so that's all of you. Study for your quiz retake. We will do it Monday. No, that should say, this is all backward, isn't it? This should say blue students, study for your quiz retake. Right? You're all gold. Yes? Okay. I have this backward. So the people who are at home, you can study, get ready for the quiz retake on Monday, and if you haven't found the altitude of Polaris, do that by Sunday night at midnight. So all of you here, in person only, should say gold students. I've got a couple of quizzes. I have the regular format like we had last time. Each section has 6 questions and a bonus. They're not exactly the same 6 as last time. They're just taken from the same Quizlet, and the bonus is not the same bonus as last time, or might be, but they're just kind of randomly selected. And then I have this one, which is the matching version. It's a little longer, but it's easier because it's matching. And you just have to match the things that are listed here with the things that are listed there by writing these things letters there. And hopefully, I haven't been through it all myself. Hopefully I didn't mess it up. I'll take it while you're taking it. So if there's a problem, I'll figure it out. And on this one, there are 34 questions. On this one, there are 30. And I've only made 10 copies of each. So if I need to make some more copies, I'd be happy to do that. And then finally, if we have time after this, we're going to do some more with the film canister submarines. But the main thing, I want to give you plenty of time to work on this. No homework, unless you need to find Polaris. Anybody have any questions out there, Tommy or Tyler?